Okay, so remember last time we got into radical reactions, and so we started to study the mechanism of this whenever the initiation step, and we finished up by looking at the propagation step, which remember was the second step that had two parts to it. First step, the chlorine radical, which formed in the initiation step, reacted with CH4 to make the methyl radical, which was the intermediate, and then that methyl radical reacts with chlorine to give you CH3Cl, and this chlorine radical is formed once again. Okay. Now, one thing we need to mention now at this point is that this chlorine radical forms, and if you look at the beginning of A can take it and do another reaction with CH4. And then another one of these can form and come and do another reaction for B. So at this point, we can say that A and B repeat. Okay? Or in a sense, what A feeds B, and B feeds A. Okay? So here we have what we can call a chain reaction. Okay? So this thing can just keep going and going and going until what? Eventually you start losing CH4 or chlorine and so on, and we'll see some other ways this thing can start coming to an end. Okay? But this is the definition of the propagation step and how the two parts of it feed each other. Okay? Let's go into the third step of these radical reactions. Okay? The third step, remember, is the termination step. Okay, so in the termination step, what we're going to do is combine two radicals. Okay? So, anybody give me an example of two radicals we can combine that form? Okay, we could do two chlorine radicals. Okay, so remember, this was our second radical reaction that was called a combination reaction. So two chlorines can come together, form the molecule there. Okay. So those two radicals are forming a bond. What would be another combination? Maybe a chlorine and a methyl radical. Okay. So if those two come together, we can form that molecule. Then lastly, what other two radicals?
CH3.
Two CH3s. So we can have two methyl radicals coming again. Okay. So these are our different combinations of termination. What is the main way that termination is different from propagation? What's being produced over here?
Radical.
No new radicals. See that? It's terminated. It's over. Okay? So once these form, there's no new radicals. So you see how with these termination reactions, the reaction will slowly die because I'm getting rid of radicals that are responsible for doing the reaction. Okay? So by definition, this is what a termination is. No radicals are produced. They get quenched. Okay? Any questions on the termination step? Okay, pretty simple. So on the exam, what I would say is draw me one example of a termination reaction. Okay? Or I might say draw me the two steps of the propagation step. That kind of thing. Okay? Let's look at another radical reaction. Okay, this one here. Let's now take propane and do a radical reaction on it. Well, with propane, what kind of products could form, okay, or what we call monochlorinated derivatives. Okay? What is a monochlorinated derivative? You see what it means? It means I have one chlorine on the molecule. So what are some different ways I can put one chlorine on the molecule? Okay? So if you take a look, I could put it here. Okay, on that N carbon. Or where else could I put it? I could put it in the middle. Give that one. Or by putting it on this end. You get that? But I have three different ones. No? What's wrong? You think that's the same as that? Yeah. Well, it looks different to me. You sure that's the same? How do I know if it's the same? They have what? The same name. Do those have the same names? Okay, yeah. So they're both 1,4-propane. Okay? So this thing here is the same as that. So I don't want to draw that. Okay? Or if you can use your mind, you can see if I flip the molecule that it would match there. Okay? I can flip molecules, just like I can flip the yardstick, and I have the same yardstick. Okay? I can flip it however I want. It's the same yardstick. All right, so this would have two monochlorinated derivatives, okay? What about if I gave you this reaction here? Could you draw all the monochlorinated derivatives for that one? How many different ones would you get? Okay, so I could add a chlorine here, 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 or here. These two carbons would give you the same thing. So I would have a total of 4. Okay? So on the exam, you would want to draw all 4 out. And there they are. Okay? It's one of the things you'll have to do on the exam is I'll ask for all the monochlorinated derivatives, and I'll even ask you to maybe name them all to make sure to you that you didn't draw 2 of the same. Okay? What's another property between each of those 4 derivatives? They are what of each other?
Constitutional isomers.
Constitutional or structural isomers, very good. Okay, I just moved that chlorine to different carbon atoms. Those are all structural isomers. Okay. Any questions on monochlorinated derivatives? Okay. All right, well, let's come back to this top reaction. And study it a little bit. Okay, if I went through the mechanism of this, I know it's a radical mechanism. So again, the first step, initiation, I know I'm getting 2 chlorine radicals produced. But the meatiest part is always the second step, the propagation. So suppose I asked you to draw the propagation step for this product here. What would you do? Well, I would take a chlorine radical, plus the propane, and do what? A hydrogen abstraction here. And so a radical would form on this end carbon. And then in the second step, I would take my radical that formed there. What kind of radical is that called again? That was the what? 3 carbon? Propyl radical. And I would react with what? Chlorine. Okay, see how it's following the CH4 model reaction we already did? So to take one of the chlorines, form a new chlorine radical. Okay, and then it can repeat itself, A and B all over again. Okay, any questions what we did there? Does that make sense? Okay. Same thing if I asked you to do the mechanism for the second product up there, 2-chloropropane. Okay, it'd be the exact same thing, wouldn't it? Except the radical that forms here would have been this one. Okay, so now it forms on the second carbon. And then down here, that radical would then produce that product there. Okay. All right, any questions on what we did there? What kind of radical is being produced for here? What was that called? Okay, not the propyl, but the isopropyl. Isopropyl. Don't forget the isopropyl group on the exam today. Remember the fish tank. Okay. Okay. Well, one of the things that when we can have more than one product forming, one of the questions we always want to ask ourselves is which one forms more, or which one is what we call the major product. Okay? In order to do that, I want to look at something over here. That we will call radical types. Radical types. Okay? Just go ahead and draw those, and we'll see what's going on here. Okay, so we have three different kinds of radicals. Note this carbon has the radical. How many carbons are on that? One. So what do you think that radical type is? A primary. Okay? Just like we can have carbon types, same thing, radical types. So there's a primary radical. What do you think the next one is? Secondary radical. Third one, tertiary. Okay, so when I have three carbons on that radical carbon, then I have a tertiary radical. There is one other type of radical that we just call a methyl radical, okay? Because it doesn't have any carbons on it. Okay? So these are the radical types you want to identify. Let's come up here and identify these radical types. Okay? What kind of radical is this one? Okay, a primary radical. How about the one in parentheses? A secondary. Okay, so pretty easy, isn't it? Make sure you can identify your carbon and hydrogen types today. So There also is a stability order with these radical types. Okay? As I come down this way to the more substituted radical, I get more stable. Okay, so the tertiary is the most stable, and as I go up, I get less stable. Okay, the reason for that, I'll let you read the book for some more detail, but what happens is this carbon here is, remember, electron deprived, missing the octet, and these carbons can donate electrons in to help stabilize that, okay? So we'll see that carbons have this donating ability, okay? Hydrogens do not have a donating ability. In fact, they are a little electronegative, which is why we have that hydrogen by the fluorine over there, okay? It's not a powerful electronegative, but it has a little bit of a pull, and so that tends to destabilize. So the more hydrogens I have, the more unstable that radical is going to be. Okay? Good to see a couple of you write that down. All right, well, let's use this fact over here and come back to our reaction. Let me ask you a question. We got these two possible products forming. Which product now do you think might be the major product? The isopropyl?
Yes.
Why do you think the isopropyl?
It's more stable.
No, this isn't more stable. This is more stable. See that? So the radical is more stable, so you would expect more of these to form to give more of these to form. Okay? So reactions tend to go in the more stable direction. So it's not the product forming that's more stable, it's this radical that's forming that's more stable. Okay? And so that's what we could predict there, perhaps. Now, let me pick up this theme of radical stability. And talk about it from another perspective. Let's suppose we had some radical that we'll just call R dot, whatever that radical is. Let's say that radical is in our body, okay? And in our body, let's suppose we had, about 5 oranges for breakfast, so we had a lot of vitamin C in our body. What do you think the vitamin C wants to do to that radical? Okay. Well, I won't draw the structure of vitamin C, I'll just keep it symbolized like this. But what the vitamin C does is it would like to take that radical, okay, through a propagation step. And so the R is now stabilized, and now the radical is in the vitamin C molecule. Okay? Vitamin C has the ability to stabilize that radical. Okay? Has the ability to stabilize it. Okay? As do a bunch of other things that we can take. Okay? Vitamin C, vitamin E, zinc, selenium, glutathione, and there's others. And these things, when they sense a radical in our body, can absorb the radical and stabilize it, okay? Or sometimes what we call trap the radical, okay? Or sometimes what we can call inhibit the radical from doing what? From doing more damage, okay? So these radicals get in our body and we can't help it. Just the general heat that we produce every day generates radicals. Or if you breathe them in through, you know, the exhaust out there, the pollution, you get them in there. So what do we have to do? We have to keep our bodies well fortified with these things that we call antioxidants. By keeping your body fortified with these, then when these things are produced, that can help keep away more brutal things from forming, like cancer and other diseases.
That's why they got so many vitamin pills and stuff.
That's right. That's right. That's why it's important, you know, to keep yourself fortified through taking vitamins or, you know, that kind of thing. Okay? Or if you get sick, you get a cold or the flu, load up on vitamin C. It's water soluble, won't hurt you, and it'll go after all those radicals that are making you sick. Okay? That's what I did. Okay? Take 10 grams of vitamin C a day. Okay? Linus Pauling took even larger amounts. Okay? And that'll get rid of your cold. This gets rid of mine in about 1 or 2 days. Okay? So, or if you're going to be around a lot of people, load up on them so that you don't get sicknesses that they might have. Okay? So these antioxidants are very important. We all get older. You don't think you'll turn 30 or 40 or 50, but it'll come.
Y'all think one of their pills have like most of them?
Yeah, they're usually not strong enough. Okay. I've done research on, if you're interested in this things, I can point you in the right direction. Okay. But you gotta make sure you're taking good stuff and not junk out there. Okay. A lot of stores offer junk. Okay. But we'll all die someday, okay? Every time you drive by the grave, we're all reminded of that. Okay. But you can make that process as less painful by keeping yourself loaded there. Okay. Any questions on antioxidants? Okay. We spend money each day on different things. Okay, cell phones and so on. Okay. Keep care of your bodies. The way you keep care of your body now will be the way that it treats you when you get older. Okay? So remember that. Okay? And also remember that sugar is the food for cancer. It really is. Cancer thrives on sugar. Okay? So if you want to help your health, stay away from eating so much sugar that can be so addictive. Okay? It is. Tastes good. Okay. So that's the end of radical chemistry for chapter 4. Okay. Now we're going to shift our attention to some other things. Okay, so remember the 3 ways to look at a reaction, or what? By way of thermodynamics, by way of kinetics and by way of mechanism, how we've been looking at it. So we've done mechanisms, and we'll look at more mechanisms later on, chapter 6. But let's go to the next way. Let's look at kinetics. Kinetics. Okay. And let's suppose we had a reaction here that we will just symbolize as A plus B going to C, whatever those things are. Okay? And let's look at the reaction using a graph here. That we'll call a reaction coordinate diagram. Very important diagrams, and you'll see these are very easy, okay? What's a reaction coordinate diagram? Well, this is where we plot energy as a function of reaction progress. Okay, so these diagrams help us to follow the reaction by what? Looking at its energy. Okay? And let's say that this energy diagram for A plus B going to C looks something like that. Okay? So over here would be A plus B, and down there would be where C is formed. Okay? So this is an example of one diagram. Let's analyze it a little bit. Okay? And we're going to analyze it first using the kinetics. Okay? So what I want to look at here, at the top of this hill, is something called the transition state. The transition state. Okay? What is the transition state? Well, if I look at the reaction A plus B, okay, what's happening here in the transition state is that A is coming into contact with B to start to transform into C. Okay, so this thing doesn't stay around too long, and we usually designate it by a double dagger. Okay, so the transition state is always signified by this double dagger in parentheses. Okay, the next thing here that we'll look at is the height of that hill. Okay, the height of that hill is what we call REA, or the activation energy. The activation energy. Okay? And write it down. It is the activation energy that determines the kinetics of the reaction. Okay, so EA is always affiliated with the kinetics. Okay. Let's blow this up. Okay, the EA is always affiliated with the kinetics. Let's look at two activation energies here. Okay. Something like that. Easy question, easy answer. Which of those two curves is showing the larger activation energy?
Right.
Okay, the right one. Pretty obvious. Larger hill. So which one do you think is the slower reaction? The larger one. It's going to take a longer time getting over that hill versus that one. So there you just learned it. The larger the activation energy, the slower the reaction. Write it down. Okay? So the larger the activation energy, the slower. Okay? You can always remember it by, it takes longer to get over a mountain than over a speed bump. Okay? Well, let's take a look at this activation energy in some more detail. Okay, we'll call this the components of the activation energy. Okay, and then we'll stop with this. Okay, what are the components of the activation energy? Okay, the first one is the collision frequency. The collision frequency. Okay? In order to get two molecules to react, if these are A and B, what must they first do? They got to bump into each other. They got to collide. Okay? So collision frequency means the more they collide, the greater the frequency, the better the chance I could have a reaction. And probably the faster it'll occur versus. Okay, that's all. Okay, so write it down, increased frequency, faster reaction. So an increased frequency would what? Always be affiliated with a small activation energy, wouldn't it? The second factor, okay, is what we can call the collision energy. The collision energy. What do you think that refers to?
Maybe the amount of energy it takes for them to come together.
Okay, or maybe we can view it this way. The two molecules come and they hit either hard or soft. The greater they hit, the greater the probability of the reaction will occur, won't it? Okay, just like hitting a nail into the board. If I just hit it tapping, it's not going to go very far. Okay, but if I whack it, okay, it's going to go in with a greater probability. Okay, so that's what we're covering here. Okay, Greater the energy, the greater the probability to get over that activation energy. And the way that we can control these first two here are by temperature. Okay? Write it down. The higher the temperature I use, what happens to the frequency of collision? It gets higher. The higher the temperature I use, what happens to the energy? It gets higher. Okay, so if I want to speed a reaction up, I use higher temperatures because I'll get higher 1 and 2 there. Okay, that's why you cook your spaghetti. So it's done in 10 minutes instead of 10 hours. That's why you bake a cake. That's why the grass grows faster in the summer than the winter, and so on. It's overcoming the activation energies. But there's one third and final factor. We'll call it the proper spot. Say, what do you mean by that? Well, let's suppose our two molecules look like this here. Suppose they had those shapes. Okay. Well, what would be the proper spot of collision where this would what have to come in there? Okay? Doesn't matter if it hits out here all day, it's not going to lock in. And that's the way molecules react. They have to hit in a proper spot. They can collide all day with the right energy, but if they don't hit the right spot, there's no reaction. Okay? And there's no way we can control that. That's just kind of a probability thing. Okay? But we can control these two by temperature. Okay? So that's what I want you to take away is when I increase the temperature, what am I doing? It's giving me energy to get over that hill. It's giving me energy to get over that hill. Okay? Question?
When you when you do raise the temperature, does that kind of control the chances that you'll get things in the proper spot?
Yeah, it doesn't. Yeah, so the more temperature I use, it doesn't really guarantee I'm going to hit the spot.
Just gives you a higher probability.
It's giving me a higher collision frequency. But it's not saying, even with the high frequency I'm going to get in there, it could hit here all day. Okay? So it's just a random thing there. Okay.
Are the frequency and the energy, are they proportional? They kind of go hand in hand?
Yeah, it'd be kind of parallel to each other. Okay. Any other things? Okay, well, let's close it here for today. I'll make a couple of comments on these.